Thank you for the introduction. Hi everyone, my name is Gilberto Mosqueda, professor at UC San Diego, and also director of the SRMD facility there. So I'm going to talk about one of the, a slightly new area of research that I'm exploring in bridges, and so this is kind of exploring this, the behavior of bridges under beyond design shaking. Actually, before I move on, I really do want to acknowledge Claudio Sepulveda, who's here, and Ricardo Bustamante, PhD students that have worked on this project. So we've been looking at the behavior of bridges under design level motion, and we know seismic isolation to be one of the most effective ways to protect structures from any type of damage. And that has been well understood, but what about when we exceed the design capacity of the system? How does damage progress? And with isolation, we try to shift the nonlinear behavior to the isolators instead of plastic engine in the columns. But then at some point, as you keep loading the structure, what's going to happen to the structure? Whether as the limited studies looking at this have shown, you can look at failure of the bearings, as some testing has shown at Reno. Or you can look at, there's been actually one test where they actually saw some yielding in the columns and showed that as you expect based on seismic isolation theory, as you begin to yield your superstructure, your periods change, the dynamic changes, and you begin to pass a lot of the damage of the energy dissipation to the structural members instead of the isolators. And so we were interested in how this changes, and in terms of loading beyond design, are there anything we could do or considerations we should look at to improve the performance of bridges for beyond design considerations? And so in this project, we're looking at developing the models, like looking at what are the limit states of bridges, and making sure we capture those types of behavior, where they include, the bearings themselves. We're looking at lead rubber bearings. Later on, we could look at friction pendulum bearings, but when you go beyond design, and you're reaching very high strain limits in the rubber, you have hardening and other behaviors that could be important, that we're capturing those effects, impact to the abutments, or shear keys, whatever may be in the way. So looking at developing models that capture the potential limit states in the bridge, and try to develop prototype models of these in open seas, to then be able to characterize the type of damage that we could expect. So this is kind of the objective for now, is really developing the models for this and trying to get an understanding of how this damage progresses in the structure, and also look at how can we improve the design, whether it's like by changing the isolator configuration, adding supplemental damping, or restrainers, and the effect those have on the performance of the bridge. So we've been working a lot within my research group on modeling of rubber bearings. And there's been, one of the more recent models proposed for lead rubber bearings is lead rubber X, that's available in open seas, that captures degradation of strength with heating. But as we've done testing at even large scale bearings at SRMD, looking at going to very large strain limits, you start to get hardening. That's probably more reminiscent of high damping rubber bearings. And so we've been looking at developing models combining the features of high damping rubber bearings with lead rubber bearings to be able to capture the behavior throughout a larger range of loading, leading to large strains, so capturing those potential rubber hardening effects and so forth. So this is just a comparison of bilinear models, which are typically used in most analysis. One of the more recent models, lead rubber X, that shows the strength degradation. And then this parallel model that combines some of the features of high damping rubber to capture strain hardening, and some of the more complicated behavior of rubber, and to be able to have a model that kind of captures the behavior from small to large levels of loading. And so just to show you, they're just simulations of a single degree of freedom system with these different models, the LSLRB, or the large strain lead rubber bearing, lead rubber X, and bilinear, and kind of showing a comparison. If you look at kind of a design level loading on the top, the model selection really doesn't matter, but as you go to very large levels of strain, the selection of the model becomes very important. And one of the features, the red lines stick out on the bottom, that's the lead rubber X model with the heating. But when you consider strain hardening effects, even in large strains, that kind of compensates. And well, we find out the bilinear model doesn't maybe do so bad after all, right? So the other area we've been looking at modeling is impact. How do we capture impact with the abutments? There's been a lot of bridge work. In my research group, we started more looking at this at buildings in the past several years. And so trying to improve some of the models like the Kumar model shown. There's a bilinear model that was developed for bridges, but trying to understand better this behavior of impact, the local impact behavior, and improve models. And so we've implemented a herd stat model now in OpenSeas to be able to better capture that behavior. This is based on some experimental data. And so kind of considering the more complicated bearing models capturing impact effects, we've been looking at developing for ordinary bridges a simple bridge model, looking at the concrete behavior, the nonlinear behavior of the concrete, the bearings, and everything combined to try to understand again how these bridges behave for design and even beyond design configurations. One area we had to focus special attention to, going back to the impact, was on the abutment and how do we kind of model abutment. We didn't find a whole lot of references on that. And so we looked at developing models in Abacus to try to calibrate a macro model in OpenSeas for the abutment that captures these kind of key characteristics of impact. And so developing the bridge model, this is just one bridge model that we looked at so far. Developed a set of ground motions, just looked at 30 motions, one for the design level, what we consider design level, the 975 return period, and another set of records at 2475 that are referred to as beyond design motions. So for these set of motions, we looked at just that one bridge model and looked at how the response compares. If you look at this bridge, so we took a bridge, an existing bridge in the literature that based on some reports from Professor Belko at Reno, and then some that was isolated. I think the isolation was modified by Constantino at Buffalo. And so we took this existing bridge just to look at how current bridges designed to current standards would perform. And for design level, again, is what we would expect. Everything works well. The isolation is very effective in that sense. But when you look at beyond design motions, you do start seeing exceeding the displacement capacity or the gaps of the specified design gaps for the abutments. So the dashed lines are the location of the abutments. In this case, you start seeing impact occurring when you go for beyond design. And for that set of motions, about 11 of the 30 motions had some impact occurring. In terms of the response of the bends themselves, you see they're essentially linear for design level loading. But when we went to beyond design loading, you start seeing, this is one of the motions we selected, they have more or less an average response. You start seeing the development of plastic hinges within the bends themselves, right? And we started seeing kind of the shift in energy dissipation going from the isolators to the hinges, and I'll talk a little bit more about that after. But before showing the overall results, I also want to talk about some other slight modifications we made to the bridge, looking at shifting the configuration of the isolators, putting stiffer isolators at the abutments to attract larger forces there, less on the bends themselves, and also adding viscous dampers. And so what happened when we added the stiffer bearings at the bends, we had attracted larger forces, stiffening. So you see the lead rubber bearing model we're using with stiffening behavior that was calibrated up to a certain level. The simulations go a lot further, and maybe the stiffening gets a little bit exaggerated at that level. That's something we have to kind of work out within the model later. Despite that, I think when we look at the different configurations, the original design, stiffer bearings at the abutments, and added damping, we said damping is really effective at reducing the displacements. In fact, gets the displacements down to a level comparable to the design for beyond design loading. And the stiffening gives similar displacements, but did have a minor reduction in displacements overall, leading to less impacts and so forth for the set of ground motions. But in both cases, we looked at one where the shifting the bearings around seemed to matter, though, was in terms of the hinge, the amount of hinge rotation demands on the columns themselves. You see in blue, this is in the longitudinal direction. You get to some very high levels of hinge rotation. Still not critical to the point where you're near collapse, but you get some significant hinging. By doing these two modifications to the design, we're able to get the hinging on the columns down significantly in terms of in both the longitudinal and in the transverse direction. Okay. So these two show to be kind of fairly effective in that sense. And these are kind of the key results I wanted to focus on. That kind of we try to summarize over our results, because one of the things we're primarily interested in understanding here is, as you begin to develop hinges in your structure, how does that mechanism change? How does that energy dissipation mechanism change in terms of transferring from the isolators to the concrete hinges themselves? And this is very important because in buildings, this has been looked at in a lot more detail. And once you begin to yield an isolated building, the ductility just grows without bounds, right? It's very hard to control ductility once you yield in an isolated building, right? Bridges, it's a different mechanism. And the theory has always been that you're going to get the same type of behavior, and you are seeing this effect, but it doesn't seem to be as significant as it is for building structures that are isolated, right? So this plot here shows the contribution, or basically the ratio of bed displacement to the total deck displacement. So showing how much the bed is taking, the other contribution would be from the isolators themselves. And what you're seeing for very low levels of shaking, basically the isolator, could take the time to engage, and most of the contribution it doesn't really matter for small levels of shaking. You could have large contributions from the bed itself, and that's okay. But as you go to design level loading, you start seeing a lot higher demand a lot of demands get transferred to the isolator, as it should be. But as the column begins to yield, and you see this in the dotted line there, shows where you begin to develop, or your hinges begin to yield in the bed themselves. You start seeing an increase of this configuration, especially when you look at the original configuration, an increase in the amount of bed displacement compared to the isolator, right? And so you start seeing the shifting in mechanism of the hinging. But again, I mean, it's still in a controlled manner, I would say. Unlike buildings where we're seeing that this just kind of seems to take off. But nonetheless, when you look at the cases with damping, damping, you're getting a lot more contribution from the band, but it really doesn't matter because the displacements are overall fairly small. You're not yielding. And then with adding, maybe having stiffer isolators at the abutments, again, you're also transferring a lot of the load to the abutment and reducing the hinging in the columns themselves. So for kind of overall conclusion from the study, where we look at design level shaking, isolation performs as expected. I mean, this is no surprise. This has been looked at quite a bit in the past. But for beyond design shaking, you're seeing the development of plastic hinges. Again, we just looked at one prototype bridge here and one set of ground motions, and there's certainly a lot more to do in that area. But this way of maybe restructuring the bearings and how we place them in the isolator, attracting more forces to the abutments, maybe one way of protecting the bends a little bit further on, and even having isolators where you could control whether it's friction or lead rubber, where you can have stiffening type of effects in the end to transfer more of the forces towards the abutments and protect the bends in this case. Supplemental damping, works great, and that's also kind of been known. What we have been looked at in detail is kind of how to manage the transfer of forces in that case. But overall, we need to look at this in a lot more detail in terms of different bridge configurations to really understand. One of the things we're kind of interested in exploring a little bit more further here is, as you have the isolators of bends, different ratios of stiffness and strength, and how you could better control that transfer of damage to the bends themselves, and have bridges that could survive these beyond design basis events and keep functional. So this is, in the limited time I have, that's all I could present for now. Sorry if I went quick or didn't get into a lot of details on some aspects, but this project was funded by Peer through the TSRP program, so thanks to Peer for the support.